So let's start our day 7 session. So in this session, we will start with gate level modeling. Wait a minute, let me take the pointer. So from this session, we will start with gate level modeling in Verilog. So what is this gate level modeling? So in gate level modeling, a logic circuit can be designed. Wait a minute. So in gate level modeling, a logic circuit can be designed by using logic gates. So we will develop the code using the logic gates. So this type of modeling is called gate level modeling, and Verilog supports basic logic gates as predefined primitives. So here in Verilog, we have predefined primitives. We have predefined primitives such as we have AND gate, OR gate, NAND gate, and we have also NOR, XOR, and XNOR. So these are gate primitives. These are predefined primitives. So before going into this gate level modeling, I want to explain the instantiation in Verilog. So basically in Verilog, there are two types of instantiation. One is name based and other is port based. Sorry, and another is positional based. So for example, if we have um, let me declare some module like module full adder input A, input B, input C, and output sum comma output carry. And here I will assign sum is equal to A XOR B XOR C, and I will assign carry is equal to A and B, or with C and B, or with B and A. So I have developed some full adder module, and I want to instantiate this full adder in another module. Say I want to instantiate this full adder in another module, say top module. Then I have two options. One is name based instantiation and another is positional based instantiation. Wait a minute, let me add one more slide here. So here, if I want to include this full adder, if I want to include this full adder in a top module, say suppose I have a top module like this, and I want to include this full adder in this top module. So I have two options available for me. One is name based instantiation and another is positional based instantiation. So let us see name based instantiation first. So I will declare some module top, and in this module top, yesterday we have seen in the simulation, right? We have declared the, while writing a test bench, we have declared the design name, that is full underscore adder followed by some name. I will take the name of the instance as FA. So in name based instantiation, we will write, we will take the individual name. For example, if we here we have A, so we will declare before that we will declare some registers in this module, say reg A, reg B, reg C, and wire sum and wire carry. You can take any name, no problem. I am taking A, B, C as reg and where sum comma carry. So here now I need to instantiate full underscore adder in my module top. So I will write full underscore adder followed by name of the instance followed by, in this full adder I have input ports as A, B, C. So I have to write the same name dot followed by the name A, and I have to instantiate this with my module signals, that is here A. Next comma dot, here I have B, so B of B, and next C followed by C, comma, wait a minute, and followed by sum dot sum of sum and comma dot carry of carry, and ending this. So like this I will instantiate my full adder in the top module. So this is one way of instantiation, this is name based instantiation. And coming to positional based instantiation, I will simply write the design module name followed by instance name followed by A comma B comma C comma sum comma carry. So by remembering the position, here we have A. So at the first position I am writing one input, and at the second position we have B. So I am writing at the second position B. Like that I am remembering the position. So while using positional based instantiation, we should be careful because we are just remembering the position of individual port and we are instantiating the module here. In yesterday's example also we have when we are developing our test bench, we are using this positional based instantiation. So we are remembering each position, like here we have at first position A, so I am using one input A, and in fourth position we have sum, so I am using sum at the fourth position. Like that, in while developing a positional based instantiation, we should be careful while instantiating the design. So while designing bigger modules, say we have 50 to 60 signals or ports, then we will generally prefer name based instantiation, because if there are these many number of signals, then it is somewhat difficult to remember all the positions of the signals, and there might be some prone to errors. So that's why we generally prefer name based instantiation if we have larger number of signals. If we have only less number of ports, then we will use this positional based instantiation. So these are the two types of instantiations in Verilog. We will see the coding and we will see how this instantiation is being made. So is this clear for everyone? Is there any doubt? Can we move forward? So here we are declaring reg A, reg B, reg C. So we can use any other name like capital A, capital B, capital C for avoiding confusion. So if you declare capital A, capital B, capital C, then it will avoid confusion. So here full underscore, wait a minute. Here in this case, outside is the one of the module full adder. So since I am using capital A with module top, so inside signals are of module top. So capital A, capital B, capital C, and outside signals are of full adder. So is this clear?
Yes, sir.
So avoid using the same signals, so there will be no confusion. So these are the we will do coding. We will see. We will check with the coding also, like how it is being instantiated. We'll see. We will check these two types of instantiation in the code also. So now let's see about this gate level modeling. So here we can see first we are developing the full adder module. We are writing code for full adder. We are writing the logic for full adder, and we are instantiating in our top model. Likewise, the developers like the one who written the language, the one who invented the language, so they have written primitives. They have written the logic for this primitives and or XOR XNOR. So they have developed their logic, and these and when we are writing this module, when we are writing our module, or when we are writing our design, when we are using these primitives, we are just instantiating these primitives inside our module. Let's see an example here. For example, module test. So here we have already these primitives are already present, like and or XOR XNOR. Let's see how to use this and primitive. And primitive is nothing but it acts like an AND gate. So we already know how an AND gate look like. So I'm taking two input AND gate. So let's say I1 I2 are two inputs, and the output is out1. So this is an AND gate. So in gate level primitive, we have already discussed that we will code according to the gate. In the gate level, we will develop the coding. So if we want to use this AND gate, there is already logic written inside the library of the Verilog. They have the developers already developed the logic for this AND gate, and these primitives are already present for us. We just need to instantiate them in our module. So now let's see how we will instantiate these primitives in our module. If we want to use this AND gate, then we will simply write and is the name of the design, followed by we should mention some instance name. Let's say A1 is the instance name, followed by first we should mention the output. This is like positional based instantiation. This is the rule that the output should be mentioned first, followed by the inputs. Input 1 followed by input 2. So here we are using positional based instantiation like that. Wait a minute. So here we are using positional based instantiation. This is the rule that we should mention the output followed by input 1 and input 2. We can also take 3 input, 4 input, like that, so on. How many inputs we want we can take, but first we should mention the output followed by inputs. So in our example, we have I1 I2 as our inputs and out1 as our output. So we will write and followed by E1 followed by our output out1 comma I1 comma I2. So what happens? An AND gate will be synthesized at the output. So like this, we will use the gate level primitives. If we want OR gate to be used in our design, then we will simply write OR followed by some name should be given for this gate. For this instance, I will take O1 followed by the output. So this is our OR gate. So for this OR gate, O1 is the output, sorry, out2 is our output followed by I3, I4. So I will write out 2 comma I3 comma I4. So an OR gate will be synthesized at the output. So like this, we will instantiate the gate primitives in our design. So this is the gate level modeling. So Verilog supports basic logic gates as predefined primitives. So these primitives like AND gate, OR gate, XOR gate, or all these primitives are already predefined in the libraries, and these primitives are instantiated like modules, except that they are predefined in Verilog and do not need a module definition. The module definitions of these primitives are already written in the libraries. We are just instantiating them in our design, and all the logic circuits can be designed by using basic gates. There are two classes of basic gates. One is and or gates, and one is buffer or not gates. So we have and or gates, and we also have buffer and NOT gates. So yeah, now let's discuss about our AND or OR gates. So AND or OR gates have one scalar output and multiple scalar inputs. We have already discussed it. This here is our AND gate symbol. Let's say I1, I2 are our inputs and out1 is our output. And AND gate primitive, if we want to use in our design, we will use the keyword AND followed by instance name, and the first argument should be our output. Here in this case it is out1 followed by our inputs. So this is the syntax for using the AND gate primitive. So the first terminal in the list of the gate terminal is an output and other output terminals are inputs. Yeah. So for using AND gate, we will use AND followed by output followed by any number of inputs. We can use any number input AND gate. And we have also NAND gate primitive. So NAND gate symbol is this. We have our inputs I1 and I2. I am taking two input NAND gate and one output. So for using NAND gate primitive, we will write the keyword NAND followed by instance name followed by output. Here in our case it is output followed by I1 comma I2. Then a NAND gate will be synthesized. And for OR gate, the symbol is this, and we have, again I am taking I1 I2 out. So for using OR gate, we will use the keyword OR followed by instance name O1. I am taking it, and sorry, not O1. I will take some other name B, like that, and I will write the output followed by I1 comma I2. For NOR gate, the symbol is this. I am taking two inputs and one output, and the keyword is NOR followed by some instance name followed by output and inputs, and the symbol of XOR is this, and the primitive is XOR. The keyword is XOR followed by instance name, same output followed by inputs. And sorry, this is not the symbol. Here the bubble should not be there. And for XNOR, bubble should be present. And the keyword is XNOR, outputs followed by inputs. So is this clear for everyone?
Yes.
Yeah, thank you. So now let's see about buffer and NOT gates. It is also similar. Buffer gates, we already know that they just simply use it to add some extra delay. This is a symbol of buffer gate. So what is the it will just simply pass the input to the output. If we pass A as the input, then output will be A. So this is a buffer gate. So buffer or NOT gates have one scalar input and one or more scalar outputs. The last terminal in the port list is connected to the input. So other terminals are connected to the outputs. The keyword for buffer is this, and the keyword for NOT is NOT. The symbol for NOT gate is this one. If we pass A, then the output will be A bar. So if we want to instantiate buffer in our design, then we will use a keyword buff followed by instance name followed by the output and the input. Similarly with the NOT gate, the keyword is NOT followed by N1, instance name followed by output and input. So like this, we can instantiate all the logic gates in our module like this. So these are the primitives available for buffer gate, NOT gate, and we have buff if and not if. So these are the symbol for buffF is like this. So we will have one extra control signal. For suppose say we have A, then the output will be A only if, so the output is equal to input only if control is equal to 1. If control is equal to 0, then output is equal to high impedance. So this is buffF gate. So in the buffF gate, we will have one extra input as control signal. So only if the control signal is 1, then the input will be equal to output. And if control signal is equal to 0, then output will be at high impedance. So for using this buffF gate, we will have the primitive buff if followed by some instance name followed by output comma input comma control signal. We have this another extra signal here. So this is the syntax for buffF primitive. And for not if, similarly for not if also we will have one more extra control signal. So only when this control signal is equal to 1, then this not gate will work. Otherwise the output will be at high impedance. So the syntax for not if gate is not if followed by some instance name output comma input comma control signal. So this is the syntax for not if gate. So these are the available gate primitives in our Verilog. So with this gate primitives, we can write our model and we can design our model. So we will develop in our next sessions, we will develop full adder, half adder, and we have a multiplexer. We will develop 4 cross 1 mux, and we can develop encoder. Encoder is assignment. Encoder and decoder are for assignments, and we have demux. Demux also you can try after discussion of this 3 modules. You can try encoder, decoder, and demux. And we have at sequential we have SR flip flop, and we will discuss D flip flop in the sessions, and T flip flop is for assignment. So we will develop all these designs with gate level model. We will directly write the code for this designs with the use of this gate level modeling. So this is all for for today's class. So is there any particular doubt or any queries? You can ask me, or else we can end the